Okay, then let's get started. Today I will start introducing you. Oh, this is the wrong one. I have to start the other one. Sorry. I divided into two parts because it's too lengthy today, getting all in once. I start about the fabrication. This is the chip fabrication as well as the packaging of the microphones to share with you. Of course, yeah, there's a lot of experience behind. And just to introduce this, I give you an old slide that I prepared sometimes at Infineon, where I talk about the innovation cycles. And of course, if you think about technology over time, you always think in this domain where we have implementation, different levels of integration of technology development. So we start very early with a very simple implementation, come to a kind of a form factor which is feasible, going to a productive form factor, then having different kind of MEMS systematics in, some we have seen already. And it is important to note that over, round about 10 years or so, or 20 years more or less, meanwhile, it is not only about the innovation cycles in the technology. So if I put in here cycles of innovation, they were in the technology in the beginning. Of course, you have to show something to customers, but then there's business innovations, tricks how to serve the customer and be finally successful to the market. And after this, again, some technical innovation could happen to improve performance parameters. Once you're in the market, you have to deliver each and every year a new performance to your end customer. Here's still the new microphone technology, which is meanwhile on the market. Always it takes kind of 6 to 8 years to really bring an innovative step to the market. And this should simply show how MEMS typically have been developed in the past. This is not much different for other kind of MEMS in terms of cycles. But what is quite important to see, if you do those developments in a fab, and this, for example, has been done in a fully productive MEMS fab, you see in those long cycles, you have to accept there's a Moore's law running in parallel, which is working on the technology nodes, the wafer diameters. And if this was initially started on 6-inch or 150 millimeter wafers in a Munich fab, which was closed then somehow in 2005, you had to transfer to another fab, which is in Austria then. At this point, when we were somehow major with the first product, we discovered that more or less the whole industry went to another wafer diameter, 200 millimeter. So you have to transfer from one to the other diameter of wafers. And Villach here, long times was very busy in producing those chips, but then comes business decisions. We see this at the end of this lessons. We see then how suddenly then is not fabricated anymore in this fab MEMS, but power electronics, and then you have to shift to another fab, so then to Regensburg, and meanwhile part of those technologies are shifted to Malaysia, whereas modern low-cost fabs. So this is always happening, and as an engineer or a researcher, you don't like this, because once you have to deal with transfer processes from one to the other, diameter from one to the other fab, it kills the innovation, and it is quite tricky in those transitions to get a new design and a new idea into a fab, while the whole process simply needs to be continued, but in another fab. The effort to develop something totally new compared to transferring something is basically the same. Yeah, and I always say these innovative, disruptive steps, they make 80% of the business of tomorrow. And this transfers only 20%. But you cannot give up on this, because you always argue also with those guys that run the business. They're really looking on cost down, price down with the customer, and this is the background for those stories. Okay, this long behind is just an example how this works. Okay, fabrication. Maybe you have been already in the clean room in Imtech or somewhere else. Everybody's fabricating those wafers. This is just an example, but the trick is get this finally into a form factor which you can solder or somehow connect to the engineering world, because there's from the substrate to those devices is a long chain. And we can sort this value chain or fabrication chain. And there's two areas. We have the front end and the back end fabrication. Front end fabrication means everything which is done, so to say, on the wafer level, and back end is everything which is on packaging, which is then bridging to the application finally. And if we go into the front end, we see we have the raw material, the fabrication on the wafer, really all the steps that you do. You end this always with testing. Also in between you have a lot of testing. We will see this later. And then if you do the testing, basically you start defining chips, because then you have for each and every chip that you test on such a wafer, you have data, and they are kind of the representative of chips. But in between comes something like the grinding and the dicing. So make the wafers thinner, then you can separate by dicing faster. This is called the so-called pre-assembly. It comes before you do the assembly. And after this, you enter into the back end. So while this part is done in the clean room, this part is typically already the pre-assembly done in a gray room or less high quality clean room, and the whole back end, of course, also in kind of particle low, but lower ISO classes. And then this we discuss later. So this is the way to sort all those processes. And keep in mind, if we were to do discussions about cost of our fabrication to get finally our device, you see that it looks like the front end is very little part of the whole chain. Yeah? And it's not absolutely wrong. Fabricating the wafer is, of course, high-tech, but also the rest is high-tech, and there's a lot of steps. And if you start discretizing your wafer, you go away from kind of a batch processing. You start manipulating and doing on single devices. And the further you come in this process chain, the testing gets more complex. So all this tells us that a huge part of the value is in the back end, even the pre-assembly, and also the costs are quite significant. And this is so important with the packaging. And we will see, of course, later on that the design that we do at the very beginning for our chip has to relate the whole backend processes already. You have to think about the testing, the dicing, the package, form factors, interconnects, etc. Okay, so this is quite holistic question, and therefore we run carefully through this. But we start, of course, with the wafer processing. Yeah, so MEMS wafer fabrication. So, and I like to start with the ideas. Each design process starts with ideas, and so do we. There's a variety of MEMS condenser technologies, like endless ways how you could do this. I showed already this patent cross-section of Mr. Sessler's idea how to fabricate a microphone with just a silicon substrate, a housing below, a hole in here, and a diaphragm which moves as a condenser against the second electrode here on the substrate. Quite simple. And if you go from there, and the next examples, you see, oh, here they have an idea. I see from this sketch, this is a bulk micromachined wafer as an electrode, and a second wafer machined and put on top of this, serving as a membrane. So it's made from two wafers. Again, an example with two wafers stacked on each other to form this complicated backplate diaphragm system. Even a third wafer to get a back cavity sealed. So many ideas. Here again, something like a systematic, and we can move on and you find different ways and implementations, so many patents. And this is just maybe a snapshot. Every week you find still today new patents filed, especially from the Asian market, for new constructions, how to do the MEMS. And everybody refers to the old ideas. Maybe the functionality is very simple. You always see here a gap and two electrodes working together, but everybody claims this process with the idea it might be better than others. And this finally is the argument to save your business with patents. Okay, so what do they have in common? Capacitive transduction, and they have bulk micromachining. So always they have this big hole in the substrate. This is very common to all of these devices. It has to do, of course, with the construction, with the modeling that we have seen before, that you need to undamp the diaphragm. So this is in common, and everything else I say is more or less is different. So how they design the diaphragm, how they do backplate design and materials, of course. The way to form the air gap is also not clear. Two wafer, sacrificial, and so on. Then is even what you don't see in here, single chip or multi-chip in implementations. And yes, this depends very much on your creativity if you do this, and you should have a wise decision how to fabricate this. And it is also very much dependent on your capabilities. Maybe you have a fab environment which is given, like the IMTech. So if you search a solution to fabricate a MEMS micro for the IMTech, you have a different ecosystem and maybe different ideas to do it than somebody coming from a highly dedicated CMOS fab. And this is basically also a reason why things can be so different and still be same quality in the result. Okay, bulk micromachining. So this is how to drill big holes into substrates or cavity etching. I give here 3 different ways how it has been done, just by technology, and then we have some examples. So very old technology is isotropic wet etching. So isotropicity is you etch in all crystal direction with the same etching rate, more or less. This gives round shapes, and the etchant that you use is here fluoric acid, the nitric acid plus acetic acid. And the reaction chain is quite complex, has to do with oxidizing the silicon and solving the silicon in this bath. And the nice situation is if you're on the triangle of those 3 chemistries, you can tweak the process. You can tweak the process for etching rate. Everybody likes to have high etching rate, but then at the same time you have to respect that you have temperature limitation, because you also tweak the temperature for the process, or you want to be selective against a mask that you need for the fabrication of the hole, which is typically an oxide, silicon oxide, rather not any kind of resist, because the resist would be still solved in this bath or not be stable. And maybe you want to stop the etching. When you etch through the wafer on the surface, you have an etch stop layer so that you don't produce the completely holes For this reason, you need to have a certain selectivity in here. Yeah. The nice thing with this process, this is a batch process. You put 25, 50 wafers at once into your bath, control the bath, and after an hour or so, you can pull out those wafers and you're done. But it is, of course, complex, and everybody knows, meanwhile, wet etching ends up with quite variation of etching parameters, wafer to edge, bath to bath. All those variations is quite sensitive and not so very well controlled. So not long after this, everybody was doing anisotropic wet etching. So anisotropic is just the inverse. We have a wet etching, which is sensitive to the surface energy of the different crystallographic directions of silicon, depending on the dangling bonds or the interconnection number of bonds in this direction. Finally, everything ends up with 111 facets, which etch the slowest, the 100 facets, which is typically the wafer surface, etches fast, and the 110 directions is in between. So people have learned this in the 80s and 90s intensively. And there's KOH, calcium hydroxide, with a very high anisotropicity, and TMAH with a little less. They are different in terms of surface smoothness. And again, you have here the same advantages, disadvantages. Of course, there's one more restriction. If you etch this way, you have a lot of design restrictions. And design is, of course, a key in your devices, and we will see it in the examples later. Yeah, and then happily, somebody was inventive at Bosch, Franz Lermer and Mrs. Schill. They invented the so-called, what we call always the Bosch process, deep reactive ion etching systematic. And just to sketch it a little bit and put here the first claim of their patent, it's a combination of SF6 isotropic etching and a fluorine passivation. So they claimed that they do an anisotropic plasma etching, so into a surface by combining this isotropic etching with a passivation layer. So in one step, they etch for a certain period of time isotropic into the depths, and then they exchange the etching by a passivation, so they put a polymeric deposition, which is not permanent on the etching surface. Then they go back to the anisotropic etching, which opens up in the area which is fronting the plasma, and then goes deeper again. And the result is, if you look at those side walls, you have this kind of a scalloped surface, and each of this scallop is one cycle of isotropic etching, afterwards passivating, and then the next step into the depths. And this gives finally this kind of an anisotropic shape. And the nice thing is, now you can define your structure that is etched by simply a mask. You are free in design. You are not dependent anymore on crystallographic directions. Of course, you pay this with a single wafer process, which is more expensive, but this can be balanced in terms of design finally. So now I have some examples. So this is really an early product at Infineon those times. This is a 10 micrometer silicon membrane with a bulk isotropically etched cavity below. So this belongs to a pressure sensor with piezoresistive elements on this silicon membrane. Very high throughput, has been produced for maybe 15 years this way, and quite successful, and even started microphone fabrication this way. This is a lot of examples of anisotropic wet etching. where we see the chips front side and back side, where we see the 111 facets. Here they are even mirror-like. Here you see the mirror, the picture of the diaphragm on the side walls just by optics, or also here you see something. If you cross-section this, you see what it means. You have a freestanding membrane, which is very small compared to the area that the chip is consuming, because you have to account for this sidewall depending on the thickness of your substrate. And then you need still something for gluing or separation. And last but not least, these are typical dry etching structures for actual microphones. You even see that it's not perfectly straight etching into those substrates, but a little bit inclined. But nevertheless, this is when the MEMS got rounded, and this was quite a fascinating story that you finally had every shape you want. Yeah, I give you a modern, and I put it in parentheses, this Bosch process. Yeah, is not really the scientific argument here. So this is a cluster tool from the company Oxford, but there's others as well. And this is like a professional two-chamber system with handling input, and all the fabrication is done then in those chambers. This is typically the wall of the between clean room on this side and gray room on the other side. And what you do in here, you take this kind of a Bosch process with this polymeric system. You can etch aspect ratios 30 by 1. So 30 micrometer deep, 1 micrometer wide. And people try even higher aspect ratios. And you etch with 15 micrometer per meter. This is quite good, but you know you have this scallop system. Meanwhile, there has been established more or less in the same machine the so-called cryogenic process. Cryogenic, this is at liquid nitrogen temperature, 77 Kelvin. And this works a little bit different. In principle, this is immobilizing the reactants, and you finally end up with a perfectly smooth sidewall of trenches. This is an example of etching trenches into the depth, which are perfectly smooth, and they have smoothness of maybe some 10 nanometers. And this is so important for a lot of electronic applications where you want to implement electronic functions such as capacitors on those sidewalls. You cannot allow for roughness. And this is state of the art as of today, and is maybe a development which comes out of these initial learnings here. Yes, I just have one picture of Franz Lermer. This was invented in the 90s, but still nowadays, here's Franz Lermer and his colleague. They get medals for their invention. Is so famous that that is from 2019, when Roland Zengler, whom you know, he did a laudatio at this event, and he was so fascinated at this time when he was in research that the MEMS got rounded, and this I like very much. Okay, yeah, and I have some more special cases, how people deal with these specific limitations. As I said, this batch processing with anisotropic etching is famous, been studied for long times and implemented even in products. And people always try to optimize safe area, because area is the most expensive parameter when you produce wafers. Yeah? And this is the result of a cross-section of a microphone coming out maybe in 2010 or so. And I asked myself, how is this produced? But you see the benefit. In contrast to what I showed before, the MEMS, the diaphragm area, compared to the chip area, is not so bad as before, because they have this special inclined cavity, and is not straight to fabricate this. So if I compare this to the classical technology, I would use this kind of a chip size, and this is 40% of saving. When you get the explanation from MEMS patent, I want to share this because I like it quite well. So if they produce all these MEMS structures, double membrane stuff like this on the surface, they have a substrate with a mask on the rear side where they start the etching from this back side. But what they implement here, they have a special layer below the critical MEMS structure. And this is made out of a polycrystalline silicon, kind of a sacrificial layer. And we know that polysilicon is etching faster than bulk silicon, the crystalline version. Yeah. And then you see how this is working. So if you start with this hard mask, no wonder this kind of a cavity will develop. So you have only these 111 facets, 54.7 degree, and you end up in the center of this structure. And you don't have released your whole MEMS. But now comes the trick that this polysilicon is etching faster than the bulk silicon, and just in a moment they etch away the sacrificial layer. And if this is starting, you open up again convex corners of the bulk crystalline silicon. And of course, this edge is not a 111 facet, and this surface is not a 111, but a 100 surface. And then you continue etching from this side, and you develop etching further and further. And even here, this is not stable 111 facets, because you still have a frontier here, is going further and further until finally the lowest energy surface is developed, which is just this 111 facet. And this is a nice trick to share how to deal with, so to say, old technology with fascinating new ideas to gain the wanted result. Okay, another example is this one. When this was announced, this kind of a structure, this is basically from the cross section a smaller membrane on a bigger cavity. Yeah, so if you were to etch straight, and this is still Bosch etching, you had only a small hole and a small chip. But for some implementations, maybe you want to have a small membrane and a bigger volume behind. So this is producing back volume with the chip. And this is what they did. And they needed to support the diaphragm in the center. And therefore, they have a kind of a two-step Bosch cavity etching. And not too easy to follow how they do this. Okay, very special ideas of doing bulk micromachining. So now we have done the bulk micromachining, which in fact comes more or less in the last process step. So do you see this? I just go item by item. So diaphragm formation. So the diaphragm is as wide as possible. There's typically all materials out of the clean room being used. For example, dielectric layers from silicon nitride, high tensile stress silicon oxide, or polysilicon or polymeric systems can be used. Yeah, and simply then you have to add an electrode on top of this, and you need to do kind of a stress control. Then you can fabricate kind of those membranes. Yeah, the alternative is polysilicon, like in those cases, which has a certain doping, or even monocrystalline membranes. But these different designs from different companies, how to fabricate membranes, and we have seen something about this. And this is an example of stress-free plates or diaphragms. Of course, you could use a silicon on insulator structures where you have maybe a 1 micrometer thin silicon, bulk silicon layer on buried oxide on a substrate. And this is such an example. You see the substrate, the buried oxide etched already, and a 1 micrometer silicon, and on top is the rest of it. But this could serve as a diaphragm if you etch from the rear side finally the Bosch cavity. The issue is it must be stress-free or tensile stress. If you start having compressive stress, you get buckling and all kind of problems in control of your mechanical parameters and with respect to air gap. Or you can even use this, the polysilicon. More or less, you don't get stress-free, but you can release it in terms of what we showed before, these floating diaphragms. Sometimes you do this kind of a carving into the diaphragm to make hinges, bending bars or whatsoever to support your stress-free plate situations. Yeah, so many different ways. Yeah, even you have kind of embossed diaphragms. What is embossing? Embossing is you have a tiny membrane and you want to have a membrane or diaphragm which is tiny to have low mass. The low mass is important to get high resonance frequencies. And you want to make it sensitive in terms of compliance. But sometimes, since we have a parallel plate condenser, it would be advantageous if all the diaphragm goes in parallel like a piston up and down with respect to the back plate. And this is what people try to do with embossing. So they structure the rim of the diaphragm and like a spoke system on top of the suspended cushion type of structure here. And this makes the stiffness of the system with, since the stiffness goes with the third order of thickness and still keeps it lightweight. And then maybe they have special spring support system in the edges where the piston is then connected to. And we find different ways like this one. They have also a diaphragm which is with springs supported all around, but then is in the center like a tube system, which is not high, but maybe some 10 micrometer or 5 micrometer only, connected to a lower layer, which gives the whole system a rigidity that it moves in z-axis with simply a piston mode. And then you have effectively more capacitive change. Okay, cool idea. So now we have backplate formation. We had the cavity membrane. Now backplate, which is the stiff electrode. It should gain electric contact as an electrode. It should be stiff or non-bending under acoustics and not bending under electrostatic forces. And it should have a lot of holes or some means to allow the air going in and out. And these are some earlier examples of so-called galvanic bridge technology. So it is a combination of resist as a sacrificial layer and resist to form then galvanic structures out of typically noble metal gold or so on top of the chips. A technology which is, by the way, very famous for RF technology. And yeah, you see thick, like 10, 20 micrometer structures, not too small in resolution. So it is limiting somehow. What you see in those designs always here, this even one out of my own fabrication early, that they have posts. So this backplate is resting on the substrate only on certain points. And this is for the argument to have less overlap capacitance with diaphragm and counter electrode or backplate to reduce the parasitics or improve the electrical situation of sensitivity and linearity. So this has also not survived because by some reason, stability of those processes is not too high. They're expensive and not standard in CMOS. Meanwhile, again, maybe in power technologies, then they are made from copper. But always we regard in the time when things have been developed. And then the big idea, how can we use SOI, silicon on insulator, or even epitaxial layers to fabricate backplates. Yeah, this has been there from all the old piezoresistive pressure sensors technologies. And in fact, this is one of the first implementations at Infineon, isotopic wet etching from the rear side, epitaxial layer, which has a different doping. So you stop with this electrochemical potential difference. You want to perforate this backplate and then diaphragm on top of this. So this was fabricated with tiny trenches, which are filled then with oxide and finally have a smooth surface to continue fabrication process. This is processes like you see here, 10 or 15 micrometer deep holes in all this plate, which were available for electronic processes. So if you do so, and meanwhile we know the result, of course, we have a limitation in damping. These resistances, acoustical resistance of tubes is so high that they limit this magenta curve, the bandwidth, to something like a few kilohertz. And then one initial idea was, okay, the acoustic resistance of a hole goes with a fourth order of radius, while a slit has only third order of the width, the critical dimension. So this gives basically one more degree of freedom, and having the same technology just with a slotted trenching would gain significant bandwidths like nearly 10 kilohertz. And this is ways of being creative with given technologies to solve a system. Okay, but of course, it's never enough. You want to have larger holes. Like in this example, this is already in SOI layer, like 5 to 10 micrometer diameter holes. But since you fabricate on the surface level, you cannot simply etch these wide holes into the surface and then continue fabricating membranes that should be flat on top. So this is something which is not too easy. And then again, it starts with tricks. So this you see here is the wafer simply, or the SI wafer, where you start doing tiny trenches. I have here a cross section. You simply etch deep, or 1 micron hole, 10 micrometer, for example. Then you have still isotropic etching. You widen the hole to get a wide trench. There's this picture here. Out of this little aperture, you can really get huge holes to undercut and open up your volume below. Of course, then you somehow have to seal this or cover this hole with an oxide, which you see in here. There's a tiny oxide covering, which, by the way, is clothing this small hole at the top. And then you produce further on this surface in terms of flat structures. You need always flat structure, flat surface to do a good photolithography. You cannot do lithography if you have big steps, then you don't gain this technology. And afterwards you etch from the rear side until you open up those oxides. Here there's this case here, you see all the dimples of oxide looking out, and then finally you remove the oxide again. And this is one way of getting those bigger holes into a substrate. Yeah, so many ideas and development flows to generate really the best structure out of this. And eventually you find this at the competitor again. So this is really from InvenSense. Meanwhile, they are sold to TDK, Epcos TDK. Their patent that they published a point in time. And really, when I saw the first SEM picture of their backplate, and this is really their backplate with this interesting structure, I didn't understand in the first case. And this is really a sketch of the microphone with the cavity, the backplate below, and the membrane on top. You even see that the membrane is supported by spring connections to the outside. And now I understand this, of course. Basically, they want to have in this thick layer wide holes But if you do the white holes, you cannot close by filling a sacrificial layer into this structure. But if you extend from the large hole these 4 pins into the direction of the center of the hole, and then start covering it again conformally with an oxide, for example, then you'll be able to close even the center of it. And then you have a little topology, but you have a closed surface, and you still see the image of this topology on the top membrane layer. Yeah, and this was another approach from other inventors to bring such a kind of a microphone technology in place. Yeah, very specific, and you never know for which reason you might use those tricks, even outside the microphone world. Yeah, another, of course, everything so far was dealing with a backplate in the lower area and fabricating a diaphragm on top of it. Of course, it doesn't play a role in the functionality of a microphone whether you have the membrane on top or the membrane below, since they are in series with the backplate. It's not really a difference. You just have to take care of the potentials and the electric situation. So next comes examples. Of course, maybe it is easier to do this thick backplate on top of the diaphragm. Yeah? And this is again this SOI membrane structure with a sacrificial layer or the gap on top of it. And here you see there's a production of polysilicon, a thick polysilicon, but basically it was formed in an epitaxial technology. So you have formed maybe this sacrificial oxide only in a certain area, and the rest outside is blank silicon, like is used for transistor formation and so on. And with this, you go into an epitaxy machine. Of course, the crystalline nature of the bulk silicon is extended in the area where it is free, and you get epitaxial silicon at this area, and all the quality would be given on top of this, so that you can still do microelectronics in this area. And that was basically the idea. But you have then encapsulated the oxide layers, but where the oxide is positioned is of course not crystalline, but polycrystalline silicon. You see this here from the cross-section. There's these grains to be seen. You see even the 111 facet developing again. The difference is the polycrystalline silicon grows faster than the epitaxial, which is more dense. This is simply to be taken into account for this little step here. Also quite good idea to do something. Finally, and most of the solutions are meanwhile done only with tiny polysilicon layers. While the upper one was still thick and stiffness comes by bending stiffness, the tiny ones are combinations of small tensile polysilicon strained in addition by maybe high tensile silicon. Yeah, if you do this and you anchor it at the side, is the end of the membrane, you can anchor those back plates nicely, or even do cutouts to reduce the overlap capacity to the membrane. There's a lot of design freedom. There's just one argument. All the stress that you put into the layer of the back plate is anchored on the substrate. And if you then cut out your chips finally, this force works on the chip edges. So it would somehow compress the chip area edges. And this compression has finally, again, a force working into the membrane, which compresses also the membrane a little bit and works on the stress level of the membrane. So this is something which you discover during the course of your fabrication and finally testing procedures. And I have yet another idea how to come along with tiny backplates, but still stiff. We have seen this trick before. if you have this T-shape structure implemented in a layer, this blue layer is a hand sketch from those times, is the backplate with big holes inside, and in between there is ridges, as I call something which goes like 5 to 10 micrometers deep from the same polysilicon. They give the bending stiffness and still allow to do the backplate tiny in terms of acoustics. And still this is a way to produce something. Out of a patent, I had a SEM picture where we see the membrane is broken away, and you look into this structure, you see this T-shapes structure like a box with a tiny grid on top. So this significant reduces the damping and gives a fantastic stability. And the trick behind is simply a trench process. If you etch into the substrate a wide trench and beside a narrow trench and even more narrow trench, and then you clad these trenches with an oxide layer here conformally, and you finally fill it with polysilicon, then the wider ones are still open and close here this forming this ridge, and others don't allow because it is already closed with the oxide. So this is ways of doing such interesting MEMS structures, which could by itself be also functional devices. Yeah, and yet another one, backplate. What you see as really composite backplates, in this case polysilicon and I believe silicon nitride. Yes, here very thick silicon nitride, basically from a passivation layer, which they use. And also company Knowles uses this combination as a dielectric backplate. And if you zoom in, you find here's the dielectric stuff, silicon nitride basically, and you see the polysilicon contact for the electrode only in an inner portion developed into the area where the holes are, as well where you do the sending of your membrane movement. So one trick in this diaphragm or backplate is how they do the edge. This edge is a complicated three-dimensional structure where this backplate is resting on the substrate, and this, as I have in mind, was invented to mitigate the stress of the structure with the substrate and get it nicely flat. So everything is patented typically. Okay, yeah. So we have all the elements, but we did not discuss the missing part, the air gap, how the air gap is formed. I always use the word of sacrificial layer technology. This comes basically from the surface micromachining technology, and a good way to fabricate tiny gaps, even three-dimensional structures. And yeah, to find this or to implement such a sacrificial layer technology, you again have to check design. So whatever you do undercutting. So you need to control the structure width, the edge rate, like the perforation of the backplate, for example, that you get a time-wise release of your structure. You have to, of course, make sure that the functional layers will not be etched while you remove this sacrificial material. So it's a question about material choice. And then all this must be integrated into your process without harming the MEMS itself or the sensitivity of diaphragms, etc. So it's not trivial, but can be done, of course. And I just have here a table with the different functions and all the materials in the clean room that I have in mind. So we want to have a backplate, a membrane, and a sacrificial layer in between. If top down, bottom up, I don't care. You have resist, imides, metals, oxides, nitrides, even silicon here for a sacrificial layer. And then we have the choice to combine those materials. So if I have decided that I want to do my backplate out of metal on a polyimide, for example, and even I want to use the same materials for my membrane diaphragm, then I can even use the resist itself as a sacrificial layer. Very simple implementation. Another way is this Knowles device. They've decided they do the backplate with the polysilicon and the plasma nitride. Plasma nitride can be etched with oxide, but with HF, but maybe not too fast. And polysilicon for the diaphragm. And then they had a BPSG. There's a phosphorus doped glass. So it's like an oxide which is doped. And this can be etched very, very fast and efficient against those other materials. So it's a working combination. Then this one is maybe a epitaxial layer, which is this diaphragm here, and the galvanic top electrode. And this is the pictures that I showed at the beginning. Then you have again resist as a sacrificial layer. So many ways of doing it. And finally, for example, this one from Infineon with CVD oxide as a sacrificial layer, because nitrides, polysilicon, they hold against this oxide. And those oxides are typically standard in the stack of metals and stack of typically used CMOS structures. Okay, various choices, and question is how can this be done? How do I get this oxide out? And there's a special issue. If we do this in a liquid, you know, surface forces and capillary forces, they attract surfaces if you dry, for example, out the liquid, because the van der Waals, the surface tension of the droplets brings the surfaces closer into contact. This is stiction. Stiction is an issue. If you had two pure diaphragm and backplates etched in the hydrofluoric acid, then you have two clean, perfect surfaces, and you start pulling it out of the bath. And the surface tension, while getting out the water, finally pulls the two devices to each other, and you have a van der Waals force which is so strong it would never release the two items anymore. And this has to be prevented. So you need to get out of a wet etching process into dry without having this surface tension issue. Yeah. And one way is to use the phase diagram of CO2. So we have CO2 over temperature. With lower pressures, everything is gaseous. If you increase at low temperature the pressure, of course, we are in solid. There's also liquid regime. But the funny thing, the phase difference between liquid and gas with temperature and pressure has an end point, which we call the critical point. At this point, you cannot distinguish between the liquid and the gas phase. And the trick is to have a process which runs around this critical point. So basically you put your wet device into liquid CO2 at high pressures, of course, and a given temperature, and then from there you start heating up and pressurizing your system, and then you go down again with the pressure at a higher temperature, and at this point then you are in the gaseous atmosphere. Those little so-called supercritical point dryer are typically done in labs, and I've also been working with such a chamber. You see here thick wall for high pressure, 74 bars typically, and I have just a little video which is showing there's a liquid phase and the gas phase on top, and at the critical point it is simply gone, the phase. So the liquid phase or surface is vanishing. And so is in the whole volume. So if I put my wet sample into this system, fill it with the liquid CO2, then maybe the liquid is dissolved in the CO2, like propanol, for example. And then you get this nice chance. And afterwards you open up, everything is perfect and dry. So this would be one way. Of course, now think this chamber for a 6-inch or 8-inch wafer or a whole batch. You can imagine this is super big chambers. I have been seeing such a device fabricated for 6-inch wafers. That was a mess of a chamber with nearly 1 meter in diameter to run the process for each and every wafer. And there was like 8 screws on top that the operator had to close each time. It's not a really productive level finally. So people are looking for something else. This is good for lab and maybe even at Imtech, but not for production. Some tricks, maybe you try to help with resistance. This is a very simple structure, maybe a membrane oxide and a polysilicon with some holes. We have been trying to release or etch oxide below those tiny holes. We can fill this with a photoresist again. In the next step, we can remove the oxide around and finally release them by a plasma etching with oxide to remove the resist again. This is a way, never really reliable, but it is tricks, yeah, and not too favorable. You can do also tricks with a polysilicon. I don't go into this. It's a little bit more complicated by one. What people try to do nowadays, or very early started to do so, was this anti-stiction bump technology. Yeah. Again, here just a simple reminder: you have a cantilever, you have this capillary force when you dry it, and this keeps the capillary adhesing to the surface. I have also a picture from a microphone. This one is a 700 micrometer diameter. And from the picture, you see here the center is sticking, gives this kind of a smiley face. And you see rings of different color, which is simply the tiny diaphragm on top is shining through. And you get the Fabry-Perot effect. So you get kind of a thickness interference pattern. So this 1, 2, 3, 4 fringes times half the wavelength gets you 1.5 micrometer of air gap in between. So you can simply control this. So this stiction from flat surfaces, you need something to prevent it. And the invention and idea quite common today is anti-stiction bumps. How can you do this? Basically, you define your sacrificial oxide, you put a tiny hole, maybe 1 micrometer in diameter. You fill again some oxide maybe on top of this to make it more narrow and to get a tip shape smaller. And finally, you can put your diaphragm material on top of this. And if you remove then your sacrificial layer, you have this kind of anti-sticking bump or dimple, like tiny needles in your diaphragm that if you get in contact with the backplate, the contact force is smaller, much smaller than total surface, and the restarting force of your diaphragm, which has here a given compliance and a spring force, it is strong enough to remove those two surfaces from each other. And then finally, it's a matter of design, how sharp, how many, how little, how those bumps you need. It's been done in very different ways. This is one of the early ones. This I've shown before. You see a backplate with tiny needles. They are really sharp, like 50 nanometers tip size. Imagine you bring those surfaces closer together, then those two arches meet each other, forming sharp tips. This is the way, or here you see posts and dimples, how they are called, which are different size. So this is an accepted means to reduce anti-stiction by construction. Then you go simply through batch processes from wet etching, and is the cheapest process finally in the fab. Okay, yeah, but there's other ways to prevent stiction as well, and this is really surface chemistry. And this goes with these special materials which are called self-assembling monolayers, SAMs, made out of those special materials like FDTF, perfluorodecyl, decyl-trichlorsilana. I cannot even read this anymore. So the one end is a fluoro end and the other one is a silanic end. So that means if you have such a molecule, you have the fluoride extension of a long molecule, which is hydrophobic, really hydrophobic. It's repelling water. The other end is hydrophilic. So if you run a process with a silicon wafer coming out of the etchant, then you have a pure silicon surface, and this is always hydrophilic. And then you expose it to this material in the right way, then they will assemble with a hydrophilic end to the surface, arrange very dense to each other, and extend with hydrophobic to the outside. And since they are only a fraction of a nanometer thick, it doesn't add really the ice, but it makes your surface hydrophobic. So if you had a contact angle of a droplet on your surface with a hydrophilic fashion, which is really wetting your surface, you end up with something hydrophobic, even repelling water if you are happy. Yeah? And this is, of course, also early guys have invented this and claimed this with a patent, so nobody else could do this. And then comes this story with anti-stiction bumps, of course. Yeah, they were early and fine enough to implement this, and they market this with these pictures. You have here the microphone diaphragm and drop it on top of this, but they don't really wet the surface. They don't go into the tiny structures. They are repelling, and the device will survive all the time. And this is also interesting later on for a lot of functionality of devices. And this patent is maybe so old that it's free again, so people might use this. And there's a good chance. Yeah, for example, in this process, which is vapor edge etching, so far we wanted to etch with water, really with HF solutions. You know? They are wet, and you afterwards go into water, you dilute the HF out, and then you dry it. But in some cases, maybe we have complicated ways, even long passes to release. And for this, people have developed HF etching with vapor. So they provide the hydrofluoric not as liquid, but as a vapor. So it's not gas, but vapor. So with water somehow inside. And if you have this, of course, you can try to do the under etching. You continue this under etching without harming the structure. It will also not stick because you have no phase change. You stay from vapor to gas, and it is still okay. But in this fashion, you can go simply also into a second process where you provide the precursors and the chemistry for this anti-stiction coating. Yeah? And this can be added to it. So in one and the same chamber, you do the release edge and you do the anti-stiction coating into the whole structure. All surfaces are cladded with this. And this gives you a very reliable, tiny surface micromachined MEMS structure, which is hydrophobic like this here, and which you can does not harm if you later on wet it, made in rain or diving or humidity condensating. So then you have a reliable structure. And meanwhile, we have at Intec also this machine available. This is being founded by the German government, and you see here the 3 chambers where you do the HF etching. In this chamber, you go from to this vacuum interchange system in the second heat-cool station for preconditioning before you go into this third module where you do this anti-stiction coating. Everything without interrupting the vacuum. Everything, of course, with a handling system can be done fully automated. And this is, of course, the prerequisite to get precise and reproducible surface micromachining technologies, not only for microphone, but much more, which is under research, of course, meanwhile. By the way, this machine is in the clean room of Hans Schickard in Villingen-Schwenningen, where we do this research, and this is part of Intec then. Yes, now we have seen so many stuff, diaphragm, backplate, substrate, the sacrificial layer, so many requirements that we have to bring together. Yeah, we have a cavity, edge stop, thinning of the wafer. It's like complex systems. We have to join this to make a process for this. And this joining has so many interdependencies. In the fabs, they call this the integration, process integration. And process integration is the key to success. Maybe even with the same items, you can have different solutions finally. And this is two ways how to stack this. I put simply for this backplate on top system, which is so long productive. You see how you do the processing. You start with the substrate. You do a top layer on top of this. You do the diaphragm formation on top of this top layer. Then you put in the sacrificial layer to develop the backplate. Then comes all the metal insulation layers. Then you do the wafer thinning, the cavity etching from behind, the release etching of sacrificial layer, and then finally the dicing. We will see how this dicing is working. But okay, there's also other ways how people have stacked those processes. Like if they start with an SOI wafer, they have to develop a backplate out of this and put the sacrificial layer on top, and then the diaphragm only before they go into the back end of line. But in the last processes is more or less always the same. You do the thinning of the wafer first, so that you have later less etching depths from the real side, because this is critical in time. Then you do the release etch as maybe the very last step of your wafer, because after this, your diaphragm, which is sensitive to contact and forces and so on, is then released. And last but not least, you have to do this kind of a dicing. And this is different ways, and for each and every system, you will find a different way to integrate this. Yeah, how about CMOS? We were fabricating all those MEMS, and everybody's fabricating more or less in CMOS environments. At least the processes are close to CMOS. Then comes the idea, yeah, we could even do somehow the electronics on the same chip. How can we combine this? Yeah, of course, it is different requirements, but there's basically two ways how you could do this. You could do the CMOS electronics first. So basically, you can also buy CMOS wafers in a fab, X-FAB, wheresoever. Buy this, go into the Intec clean room, and on the reserved areas, you do then the MEMS. You model the MEMS out of this structure. Of course, then you have to take care that you don't do any process that would harm the electronics function in here. So you do this on top. And the people that are wise, they try to reuse the CMOS technology. Yeah, there is so many layers in the CMOS processing. Can I make use of those at the same time for my micromechanics? Yes, you can do so, but then you will discover that those layers have never been characterized for mechanics. So you don't know Young's modulus, stress, and so on, because they were only used for electronics. And yeah, this process is also complex. You don't, you cannot deteriorate the CMOS process. You cannot put extra temperature budget to temper a diaphragm for stress or something. This is not allowed simply. Yeah? You are quite limited in this. And we will see now examples from different researchers, how they have been dealing with this situation. Yeah? So we call this hybrid multi-chip integration or system on a chip integration. Yeah, this is quite natural. It's just a different picture for it. Yeah, and of course later on we also discuss not only technologically how this makes sense, but also economically. Finally, there's a big question mark. So people, of course, like to do monolithic integration of MEMS. At least in the 90s, this was very famous and everybody was seeking for such monolithic integration. And this is a university example where they have CMOS test structures, maybe even for readout of the microphone. And they simply did this add-on MEMS process with polyimide microphone layers and metal layers and so on. This is all low temperature technology processes which you can add on to the CMOS. This is a very, very early implementation at Siemens. So they had the bipolar transistor process, which is different P and N junction layers stacked together, and then try to combine a pressure sensor process and even use the gate of the CMOS portion. So it was a bi-CMOS process, bipolar plus CMOS, a very complex process. And then this could be the diaphragm and some oxides or passivation be a secondary layer. Well, this is more than 30 process steps, and I can tell you it's not really been working. The simplified version of this was finally only to integrate a junction field effect and transistor to do the minimum functionality of the electronics, to transfer the impedance of the high node into a low impedance node for the later electronics, or directly to some audio interface. But even this is finally so complex and so many interactions in developing this process. Okay, transistors were functional, but yeah, a little nightmare to develop this. And here is even a not too far away from 2015 report from a Bosch company, Acoustica in US, that really a CMOS process implemented here with a membrane structure inside. We will see later on. And now what do we see here? We have here 25, 12%, 40% usage for the MEMS in those chips. So I'd say if the MEMS is very small compared to the ASIC, it could be maybe even feasible. But at the same time, you have this complicated MEMS processes on such a small area of chip. So cost-wise, this has to deal something with each other. Yeah, of course, we have an example. This system here, this Bosch Acoustica system. We cut into this structure here between the electronics and the MEMS portion. What we see in here is the cavity by a dry etching etched into the structure and then stopped by time. This time you see at this dome shape of etching front. And of course, this is critical. If they can't control the thickness of the wafer or the timing of the etching process, the backplate will be thicker or thinner. And then we see here, this is the backplate. You see how this nearly isotropic etching is ending up. And we have now a nearly 40 micrometer thick backplate with 13 micron holes inside. I don't remember how they do the holes. Yeah, they do it maybe from the front side. And this is not an ideal situation for an undamped backplate. But at the same time, you see here, there's the microelectronics, the CMOS layer, and one of the layer is used for the membrane. How did they do this kind of a membrane? Yes, on this slide, you see here the edge of the membrane here. There's the passivation layers, there's metal 1, metal 3. and they have a kind of a meshed membrane. This is a fascinating idea. If you look at this, is one layer, I believe it is a one polysilicon layer, which has all this kind of a meander structure, which is interconnected, which is with each other. It is finally nearly closed, you see here, but segmented, but acoustically nearly closed, and it makes a soft membrane. And the air gap, which is here closed in this preparation, the air gap is formed by etching through this meshed structure with a gaseous component into the substrate for some 5 micrometer or so, forming the gap below this meshed diaphragm. So this is a cool job, super inventions behind this, but everything is isotropic and depending on time-wise etching and quite limited. Yeah. So the question is, did they survive with this? Did they really make a business in here? Yeah, and then we come to the other side for the discrete or hybrid integration. Yeah, systems in package, so to say. Then at some point, at least I understood, everybody was clear with this, you better optimize the MEMS on a MEMS process because you are free to do whatever you want, and you connect it to an ASIC designed for this, maybe not as integrated, but with wire bonding, for example. And this one does the right job to the interface to the outside world. Maybe automotive, hearing aids or whatsoever, or mobile, you can choose. And if they change a technology node in the electronics, I don't have to change my MEMS process because this comes on plus. Remember the first slide. You change a technology node, you have to reinvent your MEMS technology. And this is separated now and finally successful. And even you see again Acoustica coming from this really nice and small chip scale integration. They finally jumped to 2-chip solutions where they have a MEMS, which also you see here is now bigger. The diaphragm is bigger, so it tells me something about performance and a separate die behind. And different competitors come to the same idea. This is a flip chip version, basically. You see only where the bumps are, and they flip it, and this is the company Knowles. So this is something which is finally successful. Yeah, the question is, why is this successful? Not only because of technology, but also because of economy. And this finally I want to share with you. If you check cost of something, of a MEMS system, I would say I can do a rule of thumb. The cost is proportional to the silicon area, first of all. This silicon area have to weight with the complexity of the process in some case, maybe the number of process steps, maybe the number of photo layers that I use. Yeah, so this brings up the cost, and the yield will the higher the yield, the lower the cost. So yield is basically the number of good devices out of the higher the yield, the lower the cost. So if I have low yield, say I only get 50% of good dies out of my process. So then, of course, my costs are high because I have to pay also the area that is bad in all my fabrication. So this is a rule of thumb to judge for cost. And then I compare a discrete with an integrated fabrication. So how can I do this for a discrete estimation? So the MEMS wafers, I judge here. So the chip itself maybe has 1.2 millimeter side length. I know you can fabricate it maybe with 11 photomasks. This is my complexity. And the yield, okay, this depends whether you are a starter, you're in a good ramp up, or you're in an established high level of yield. So finally you have maybe 95% of good dies. So what I do now, I simply multiply those numbers. I don't regard the unit, so it's just a number. And if I multiply this with 50, I get 32. The higher yield, I get a lower number, or 95 is 17. This is the cost of my process. And of course, I also need an ASIC process. The ASIC is smaller than the MEMS. It needs more mask to fabricate, but it has a fantastic high yield. This is a standard established process. And you see here comes an 8. And it's of course not absolutely right, but see, the ASIC is maybe only half the cost of a MEMS chip. The total cost, I simply add up those numbers, I get these numbers. Now I do this for monolithic integration estimation, yeah? And I do some assumption. I assume that I have so much free area around the membrane, on the rim around my membrane, where I can fit in all the ASIC functionality, so the transistors are all around. Somehow I bet I can do this. So I allow to have the chip the same die size as the MEMS only. So this should be really a benefit. But then I have also a good judgment. I reuse some of the layers of the CMOS process. So I don't add up 20 masks from the CMOS plus 11 masks from the MEMS, but I maybe have only 5 additional layers. So my complexity is 25. So, and if I start then the multiplication, then I have to multiply the cost of the MEMS and of the ASIC yield, yeah? And this yield multiplication, the ASIC always 98% yield, very high, but the MEMS portion on the wafer maybe only 50% at the beginning. And this, of course, loads the total layer, so the total wafer. So it comes out with low yield. So finally, I get then initially maybe a 73. And even finally, if I'm very, very good with my MEMS yield, I still have a high cost number, ideally, which is nearly double that of the discrete solution, yeah, if I compare 25 to 38. So this is finally the reason why it is better to do two-chip solutions, especially for new technologies with risks. So we can separate the risk from each other. And this finally gives you a reason to have hybrid integration of MEMS systems, whether it be, and you find this nowadays, whether it is inertial sensors, gyroscopes, microphones. Maybe there's a way, if you get a very intelligent new MEMS microphone idea, which needs only very little space on your CMOS and can be ideally realized with those MEMS structures. Maybe there's a chance and a way in the future to come back to chip scale integration on CMOS of such devices. Okay, this is the final little economical judgment here on those structures. And last but not least, I have here a YouTube video which you can watch offline again. I simply show in here is a little, oops, I don't know whether it's opening up. Yes, it's opening. It's like 8 minutes.
Infineon Technologies is one of the world's leading providers.
So this is basically a process or a video from Infineon in Austria, where we see all these fab buildings. With the entrance is a grown fab with so many different buildings connected to each other. But I finally wanted only to show you how you see those MEMS wafers are fabricated. Where's the microphone? You see basically it's at 5 minutes or so. Different wafer diameters, of course, fabricated on. Yeah, here we see then basically the MEMS fabrication.
Micro electromechanical systems, or MEMS, have been produced at the Villach site since 2008. MEMS are used, for example, as tire pressure sensors in vehicles and in silicon microphones in smartphones. Production of MEMS is highly demanding since the...
So what you saw in here simply is a picture how they do the on-wafer testing. They connect like 60 microphones in parallel and they ramp up the voltage up and down again. And they produce this electrostatic sticking and release again. And this is the electrical wafer test where they show it. And here you see some Bosch cavity edges from a certain device. And so you can look it up afterwards. Okay. With this, I'm at the end for today, because the whole packaging or pre-assembly, what comes now, we are only at this level. I was discussing a little bit of the integration, but this is a chapter by itself, the fabrication up to the application level of microphones. We can discuss them in the next lecture. And with this, I would end now this story here. And sorry if I talk too long, but still you are welcome to ask questions. Okay, if not, feel free to ask questions later. I have to stop.